Good afternoon, everybody. First of all, I would like to appreciate the opportunity offered by the Energy to participate in the Global Energy Simulation Summit. I would prefer to present this in a real meeting room, but with the actual situation around COVID crisis, it has to be virtual. And here I will leave a personal reflection. Do you think that real events will have the same relevance once the COVID will be under control? So the purpose of this slide is to share some concepts about the GE-Hitachi branch. GE-Hitachi is an alliance created by GE and Hitachi. This joint venture basically increased the value curve for our customers, combining the GE nuclear expertise and the Hitachi proven experience in advanced modular construction. Those attributes together position strategically to GE Hitachi for the new nuclear market. In addition to this, some data just for reference, actually GE Hitachi has 1,700 employees and it's separated in 3 different business lines: nuclear products, nuclear parts, and nuclear services. The virtual reality innovation platform that I'm going to present you in the next slides has been developed within the last one. So after the brief GEH introduction, let me move to today's topic, the GE Hitachi Virtual Reality Innovation Platform, and let me briefly explain to you how this technological revolution started. By 2018, I participate in the World Nuclear Exhibition in Paris. It's a really big nuclear event where majority of global nuclear companies are represented. During the 3 days I spent there, I discovered that at least 50% of the booths in the exhibition area were using virtual reality. It captured a lot of attention of the visitors who were very interested in participating in that kind of activities. Even I had the opportunity to put my hands on some of them. And when my first impression was very good, again, it captured a lot of attention. Second one was much more poor because when you try to go farther on the content and the applicability to real world, you discover that the initiative was a pure marketing strategy with no real content behind. At this moment, I made a decision. I had to be able to get virtual reality added to the GEH portfolio of solutions, but not just from a marketing point of view, but with a real application to our real life and with a real and justified return of investment. Not only from financial perspective, but contributing also to improve our digital footprint, our company sustainability. The travel started in Paris, the city of love and light, and this is what I felt during the World Nuclear Exhibition. I immediately fell in love with the virtual reality. Once I back to Spain, I kicked off some data mining initiatives looking for other industrial applications that could be used like reference for the purpose of applying virtual reality to the GE Hitachi business. After the benchmarking effort, I found one that was very interesting, not only from the application of virtual reality point of view, but for the kind of training it has associated as well. It was very similar to our necessity from criticity, high specialization, and cultural demands point of view. The case was the flight simulator used by the commercial aviation pilots to justify flight hours, avoiding the necessity of flying real planes for it. My second effort was looking for actual virtual reality technologies available in the market, with a clear picture in my mind. I was looking for a technology able to let us fully replicate our real-life works, with no limitation from physical usable surface or from number of users working together points of view. This point was resolved in the more unexpected way. By that time, I was in the middle of an MBA after 24 years working in the energy business. I was looking for other reference to help me refresh perspectives, reestablish priorities, etc. One of the days, one of my colleagues in the MBA came to me and started to explain about a virtual reality company owned by his brother that by that time was working for Hitachi in a nuclear project. I asked him to be introduced to this company, and as soon as I put my hands on the technology, I knew that this was going to be the solution I was looking for. It was a just patented technology beating all the traditional virtual reality technology limitations. With the benchmarking successfully executed also in this area and the virtual reality technology identified, I faced the more difficult part of my personal challenge, find the opportunity to do a demo to our leaders on the virtual reality capabilities. But finally, I identified the fuel movement simulator opportunity, and after some discussions at different levels of our organization, I was able to get the funds to go for the fuel movement simulator proof of concept test. So after the work to define the challenge, to build the opportunity, and to define the project, in February 2019, we kicked off the fuel movement simulator proof of concept. It was very successful from the early development stages. The project was developed under agility methodology with different sprints, each one of them validated by the GEH Fuel Movement Committee. Each one of the validations opened to me a wide number of possibilities to apply this virtual reality solution. This was based on the brainstorming sessions that spontaneously occurred on each one of the closer discussions, having VirtualWare and GE Hitachi team members discussing on different perspectives, different features to be added, different options to enrich the final product, to the point that right now we are not working on a single fuel movement simulator. So in this slide, I'm sharing a video of the GE Hitachi boiling water reactor fuel movement simulator proof of concept. It was recorded during the factory acceptance test in our technological partner facility in the north of Spain. First part of the video is the training introduction, explaining to the trainees how the virtual reality pill will work, the different ways they have to interact with the virtual reality to move fuel, to get access to documents, to mark them, etc. At the end of the video, the real plant configuration is appearing, just to give you an idea of the level of detail we put together into our solution.
Welcome to the BWR Nuclear Reactor Training. You are in a waiting room where you will perform different actions to get into the virtual environment. In this session, you will perform as this follows. On the floor, you will see two lines. They delimit the area of the bridge where you will use. Go to that area and walk through. All right, we're all ready to work here. You will have the movement sheet on your hands all the time. Extend your hand to visualize it. Perfect. Now bring on your fingers to form the place. Great. You are ready to start the training. Now wait for the driver to start the signal. Get ready. The training begins. 3, 2, 1.
So very likely you could be asking why we are revisiting the Innovation Hub. The explanation is simple. The field movement simulator proof of concept was just the beginning of an incredible innovation travel started in 2018, but without a clear end date. The reason behind is that at the conclusion of the factory acceptance test, we performed an internal brainstorm event looking for options to escalate the applicability of this technology. And in the next slides, we will present some of the things we have ongoing and some of the new projects we are considering. Let's start with case one. Let's talk on the actual evolution of the field movement simulator. What you watch on the video was the field movement simulator proof of concept. Actually, we are working on a new concept, the dynamic field movement simulator, with the ability to replicate whichever of the actual boiling water reactors existing on the GEHOEM fleet. To achieve it, we have introduced 4 grades of flexibility to be configured at the beginning of the training experience: contention design, reactor design, field movement bridge design, and field movement console design. This last one is physically replicated to get our field mover walking over it like in a real power plant, while following the evolution in the virtual reality. Another very special attribute of our dynamic field movement simulator is that it's not only having tactile feedback. With the new mass design, after the virtual world visit to our San Jose facility, we have been able to add the haptic feedback also. But this was just the beginning. As far as we did dive on the virtual reality technology, we continue to discover new opportunities to apply it. Case number 2 is very interesting. During the field movement simulator development, we discovered that the virtual reality was not only good from processes or procedures replica point of view, but it also offered you, for example, the opportunity to reinforce important cultural aspects during the training. In this arena, we have developed a foreign material exclusion training pill, and we are on the development of a supervisor training pill for lifting maneuvers. But this was not enough. While analyzing the usability to train and reinforce the GEH workers' culture on certain areas, we discovered a new use. The case 3 describes how this technology can be applied to engineering works like design review, prototypes creation. A good example is the well done that the former US Secretary of Energy did on the first X300 full-scale virtual reality mockup during his visit to our Wilmington headquarters in North Carolina. In the next slides, you will have the opportunity to watch some videos of these new concepts. This is our foreign material exclusion demo video. It's very fresh because it's not just permitting to train on working skills to search for the foreign objects introduced on purpose on the system, but it's also asking to understand which is the potential risk for the core, and it's requiring the operator to recover it. So next video is a demo of how virtual reality can help you to easily put together complex full-scale mock-ups to perform very realistic design reviews, avoiding the necessity to build costly physical mock-ups in project early stage. At the end of the day, is the demonstration that virtual reality innovation platform can be also applied to engineering work. And here again, visiting our innovation hub, and it's not a déjà vu. On every innovative project, you need to pay attention to all the different opportunities to pivot on your strategy to enrich the solution value curve. You remember that the travel started by 2018 in Paris, but 3 years later is not even close to finish. Each step we do open in front of us a lot of different options to be explored, looking for ways to differentiate our company from our main competitors. In this race, we identified another 2 opportunities to make our technological platform more accessible and more useful. The case number 4 was to create a hardware solution, making our virtual reality innovation platform deployable. We achieved it by the end of 2019, and we presented during the Spanish Nuclear Society meeting. We exposed our deployable virtual reality solution to all the country chief nuclear officers and site managers, and even to the Spanish regulator. And the validation was so successful that by that time, our top leaders explored the option to get it deployed to an executive event celebrated at Pinehurst. And the second one, the case number 5, was focused on the D&D business. Everybody on the nuclear industry is aware of the big opportunities on the D&D niche. But all those opportunities are low added value. At the end of the day, are works associated to a process to scrap the power plant. So typically, our opportunities linked to reduce contract margins and consequently need an innovation to make them more attractive for customers and more productive for companies. In that arena, we are exploring the D&D virtual reality simulator that will enable our team and customer to train on the reactor vessel segmentation before even to have the real primary segmentation station. This is the cutting tool built. In this slide, we are going to watch a video showing the evolution of the assembly of our deployable virtual reality room. Complete evolution is around 8 hours, and the video is just about 1 minute. Next video is a short evolution of our D&D simulator. The concept is the same than the one for fuel movement simulator, but the complexity is bigger, depending on the lifting maneuvers, the weight of the components, the size of the primary segmentation loop, etc. The principal value is that it's the first solution permitting to train the D&D operators in a real environment equal to the real life, but with no risk. So here again, another visit to the Innovation Hub. And right now you might be thinking, another time in front of this slide, what can be the next? I promise you this is the last time, and I'm going to explain you why we are here. The reason is simple. The virtual reality has been just the first incursion in the new digital technologies, and it has opened our mind to explore the application of others. Actually, in the case 6, we are exploring an opportunity to build a D&D lean optimization tool. The purpose is to combine our knowledge and D&D empirical data with virtual reality, artificial intelligence, project management software, together with machine learning and agility methodology. What are we pursuing? We want to create a software solution able to import 2D and 3D drawings related to the components to be segmented. The software will have customized algorithms that will outcome with the first draft of the D&D cutting and packing plan just based on internal computer work, avoiding the necessity of thousands of hours of engineering. A virtual reality platform able not only to train resources, but to validate the draft of cutting and packing plan, and not only from dimensions and weights point of view. We are exploring also the opportunity to introduce dose rates, surface activity, and other factors. Summarizing, everything based on physics can be addressed by our solution. A system to do an effective project follow-up when comparing planet versus execute, but at the same time able to create big data clouds that will be able to be friendly navigated in the future when looking for additional opportunities to optimize and increase productivity. And last but not least, opportunities to continue improving our cutting tool. For sure, here you were very excited about the opportunity to watch a video presenting this, but you must understand that this is a complete new concept, and unfortunately, we have not able to put a video in this phase. So, thank you very much for the attention. I hope you could feel my passion during the presentation. After 3 years developing this solution, I consider the virtual reality innovation platform like my small kid. I'm a real virtual reality believer. I'm a digital pioneer, and I'm convinced of the technology value and how big is going to be the disruption created by it. So we have only one option: evolve or get extinct.
Good afternoon. Thanks for having this session and for inviting me from ABB. I hope you all are well and safe, and I will start the presentation now. So I will talk about simulation of digital twins for increased safety and productivity and efficiency, and look at what we can do on testing using simulators. So ABB has been a technology leader for many years. It started in the late 1800s, and when we offered solution, it was local operation, and now it has been a journey. You could do remote operation, and we go more into collaborative operations now, and towards autonomous operations and operative support. So what we are doing now, we have a very good control system, our ABB Ability platform, where we have a very good structure for objects and assets and how to control and supervise these. And we and many other vendors and our customers are looking at how we can do the engineering as efficient as possible. So we do our engineering, a lot of it in cloud. It can be customer cloud or public or private clouds. And we also support in having very good collaborative environments so that we can support operators. And in this, we also see more and more that digital twins, or also called sometimes simulators, are very important to support the customers to have reduced risk and increased efficiency and operation. So what we're working on also for the future is a lot of things. And we could mention especially the phase that the customers are having the marshalling. Now it's more and more going over to digital marshalling, so we can do a lot of testing of both control system and equipment before commissioning. So the commissioning is starting up earlier and shorter time on commissioning. And also now that a lot of data is more and more accessible, it is now also important to look at what we can do on artificial intelligence and what we can do on machine learning to take the data from devices like a valve, for example, to see what the status is and how it could be operated more efficiently, or if something is going wrong. So we are looking into big data analytics and using the open standards and that are available. So what we are talking about is a control system for a plant. So the plant is producing a specific product, and to do that, we have an automation system, a control system that is supervising and controlling the process, so that more and more is done now automatic. And to support this, more and more customers have simulators. And what is important there is that you could have either a digital twin of a device, or you can have combine it with the control system, so that you have one or several digital twins actually. But looking at the simulator for this plant, you would, for example, have a replica of the HMI, you would have a replica of the control system, and put that onto a standalone simulator. And instead of the process dynamics, the control system would be stimulated with dynamic values from the process model and being controlled by the instructor station. By that, you have a digital twin or a simulator. So what is a digital twin? You can say that, for example, the twin is the devices, and they are connected to the control system. So then you have a control system digital twin, and you have the asset data that you can also combine it with. So then you have the plant objects. And for the control system, to be able to run in simulation mode, you need actually to add some simulator commands, so it's possible to operate this simulator. And you need it to run faster and slower than real time. You need to load initial conditions and save initial conditions, so that you can do and run scenarios over and over again during test phase or during training, for example. So these commands are then added to the control system. So by that, you have a digital twin of the control system that can run in simulation mode, and you have a digital twin of the process and the electrical dynamics. And by that, you would have one digital twin for the whole plant. So you combine the control system in simulation mode with process model or electrical model. So this, then you take over to the plant life cycle. So on the right side here, you see the plant life cycle typically. So you go from the design phase, build how to build the fabric, do analytics and design and fix values, how you want to build this factory, choose a control system so you can have a good automated production, and you prepare for production start, go into operation, and perhaps there needed some modifications. If you look at the simulator, then again, you could have one or several digital twins. Some of them could be combined into a simulator, and you could have one or more simulators running in parallel throughout the plant life cycle in the different phases. And I will come back to that a little bit later, what that means for the types of simulation and the level of simulation that you would need. So first, I would just like to mention something about some definitions. So what is simulation? So what we often talk about when we have simulators for automation systems and for plants, we have stimulated versus emulated. So what I'm talking about here now is stimulated systems, where the control system is identical to the real plant. And with the control system, then I'm talking about the process control system, the emergency shutdown system, the process shutdown system, and also the fire and gas system, and also perhaps also the power management system, and that it is identical to the real plant. And also the operator environment is identical. So they have the same HMI that the operator meets every day on the plant. That is also then stimulated. It is identical on the simulator. And when you compare that with an emulated system, then the control system is kind of programmed. It is different from the real plan. It is simulated. You don't have the same control system that you can copy when changes has been made. Then you have to program it when it is beneficial. And the operator environment is also different. So for example, you can compare what you would have of a simple game on the PC. You can say that is emulated. You don't have the same panel, or what you see in the real world isn't the same thing. On the stimulated system, you would have exact replica of everything, actually of the chairs and the cabinets, everything. Here you see a plane, and the HMI is exactly the same. So when you test the real thing, and when you train the pilots or the operators, they are then sitting in the same environment. It's very easy to know how to operate then when you are trained on the simulator, because it's the same when you come to the plant. So what are the challenges that the production plants or dynamic processes have? It's a lot about avoiding risk and minimizing the cost, and to increase or have the right performance to produce the right product. And there you have different kind of challenges. For example, now a lot of the experienced operators on the plant, they are retiring, and how to capture that good knowledge, how to transfer that to the new operators so that they can learn from the best, and how to capture that the knowledge that you can do and put into a simulator so that you can use a simulator learned by the experience or taught by the experienced operator. You track that in the simulator, and then you can use that for the new millennials when they want to work on that plant, for example. And what about when new processes are introduced? It would be a good thing to see, to check that out on the simulator, to see that the production actually is according to what is expected, or if something should be changed. So if you look at also unplanned downtime due to operator errors, there's a lot of losses every year due to unplanned downtime. And a lot of them, it's 40%, is actually due to operator errors. And if you look at the figures there, it's 40%, and that means $80 billion every year. And there are several things that can be done to meet that risk of losses. It is to increase automation level. It is to introduce good alarm management systems, for example. And it's also to introduce simulators to do better testing and to do a lot of training of the operators. So that's a good thing with humans. They can be trained. And we also like to test. And what we have seen is in many years now, we have been using simulators for different purposes, and we have done a lot of test validation of the design on the engineering simulators, and using high fidelity simulators for DCS checkout and operator training on simulators, and actually also using simulators during risk and hazard training. And especially during modification and before upgrades, it's very beneficial to use simulators to find out if the optimization is according to the plans. What we have seen lately in ABB is that it is very time consuming to make a high fidelity model. And why not create some tools that we can use earlier in the early phases during DCS configuration? So we have seen that we can save a lot of time by having some simplified test tools that we can use during control system implementation and integration. And the same tools can also then be used for operator familiarization with automation HMI, and how to use operator displays, how to navigate between, how to acknowledge alarms, and actually also see that some of the configuration is optimal and as planned. And then when you go to virtual commissioning and integrate with a high fidelity model, the real control system in simulation mode, and also integrated then with a high fidelity model, then you are much better prepared and have discovered things earlier. So when you go to virtual commissioning, you save even more time, because you can do a good checkout, but you have found things earlier. And as early as you find things, the more you save before operation, in both time and in value. And the same simulator or a second simulator is then used for operator training. Sometimes engineering simulator and the operator training simulator are different, depends on the use cases for the end customer. And optimization with high fidelity model is also really beneficial. And of course, to get the most benefits, you need a high fidelity simulation for training and for testing, but different cases in different life phases. So what we have done is, again, looking at the test phases. We have seen that we could actually generate automatic object generation of the control system. No, I was wrong. we can actually look at the control system structure, and we can create simulator objects that matches those. So then based on the control system structure in the real control system, you have an automatic generation of simulation objects so that you can test the control system on that. And then you can test the process control system, the emergency shutdown system, and the process shutdown system, fire and gas system, with this I/O and device feedback. So it's I/O by I/O and device by device that you can test the control system in the early phase. And when you're finished with this testing, you can just disconnect. You don't have to do anything with the control system. It is as it is planned for, and you don't have to to plan for that or make sure that you reduce things. You just use the real control system and connect automatically with I/O and device feedback in this low-level simulation tool. And with that, you can do actually virtual FAT. So we have some customers that saw that this was really, really efficient and that they saved time and you had a good user interface. It was easy to change values. For example, the valve and the transmitters are set to default good values and for example, 50% opening for the valve. So then the user can set values and test that the faceplates are changing accordingly and also the control logic. Especially sequences are important to test. Startup sequences, shutdown sequences, operating procedures. A lot of sequences are used in the control system. It's really, really hard to test without a simulator. Actually, there's a lot of benefits here. Protocol testing is also a bit challenging. And then by using such a simple tool and also to store the configuration for later reuse, it's really easy then later to manage with changes in an efficient way. And the next step, you can see that you can look at the closed loop testing. So then you can combine the valve, for example, when the valve is opening, you can set that the level indicator or level transmitter close by for that loop would have values that are aligned. And with that, you had done the I/O by I/O and device by device testing. Now we can go to the next step. You do the closed loop testing. So you can test loop by loop. And then you test it, for example, every loop around this tank, for example. As I mentioned earlier, this can be used in the early phase of the project of the control system development to be used for operator familiarization of the HMI and libraries also before combining with high fidelity simulators and get even more benefit out of this setup. And then you can also connect loop by loop, so then you can have the larger topology or the whole topology of that production plant. And then you would have a setup of simplified simulation, easy to set up and configure, and also easy to disconnect. And then you can use this for a full process FAT. And as I mentioned, high fidelity is also really, really important. So when combining with a high fidelity dynamic process model, combining that with the control system, and also to combine with a high fidelity electrical model, then you can have a full system digital FAT of both the safety and automation system. And it's also a perfect place to evaluate the design data and both of the equipment and the settings, and look at the OPEX and the CAPEX of this production plant. It is reduced. And by testing do a DCS checkout of the control system and the design on the simulator with high fidelity modeling, commissioning time is reduced. So 3 weeks of saving on commissioning in time is not very uncommon. It's actually very often what we see that is saved. And also the simulator can be used for dynamic tuning for startup. So you can tune the PID regulators, for example. Really, really efficient. And by adding also the electrical model to the plant simulator is very important, because if you don't have the electrical model, then you would have actually 30% of the plant missing. And the electrical model with the simulated generators, automatic voltage regulators, the breakers, and the protection relays. So then you can also look at how the power management system is running and to avoid the blackouts. So the operators know exactly how to trust the power management system, how it is working. And by that, by having a plant simulator, the operators have a full view of how the plant is to be operated and what to expect regarding the production. And as I mentioned in the beginning, we went from having equipment running on the plant, everything being remote, for example. What we see is that going from physical simulated delivery and service and clients, now it's more and more virtualized. So some years ago, we did virtualization and could run several virtual servers on one physical machine. So that's helped to reduce hardware and footprint. But now more and more we are also having virtual simulated delivery. So we can, for example, send on a disk so it can be implemented in a private cloud of a customer, or it can be a full virtualized system that it is hosted in a public cloud. We could also give full remote access, and the customers could get access to a permanent system or to a system for a shorter period of time. So it's more like a subscription base, and by that, no hardware is needed. So it's getting more and more flexible, more and more accessible, and of course, cybersecurity also needs to be ensured. So I would like to share this with you. This is a project, the different project phases of the automation system and the simulator systems, going from left to right. So, for example, what we see that if you use simulator in the design studies, you would, for example, look at what kind of motors and generators you would have for that plant. And what we have seen from studies we have had is that by looking at the equipment and not oversizing, for example, but looking at the long phase production that is needed to produce a specific amount of pulp, for example, we could see that the customer could reduce their capital expenditure with as much as 20 to 25%. That's a lot of money. And then if you go into the early phases of the process automation system implementation, normally they are implemented in a different process section, and by going from design input to do the control engineering and have this automated feedback that I mentioned in the beginning with the IO and device feedback, it is as much as 40% testing time that can be reduced. So that is kind of the focus for this presentation, to also how to do testing and how to save testing time. So there's a lot of things that can be done with good tools, reducing testing time and shorten project execution time and being more competitive. And then again, we can do the same with the power management system. So we have this electrical model going through the design phases, doing the control engineering, and do the application test on the electrical model. And why not actually doing implementation of the control system or the power management system on the simulator, because then you have the benefit of having the modeling and the tools ready. So then when you have passed FAT, everything is ready. If you have you're going to deliver an operator training simulator for the process and the plant, you would combine with a high fidelity model and then do this integration, do full virtual commissioning on this simulator and save commissioning time. That's really, really beneficial. As I mentioned, you can also use a simulator to reduce downtime. For example, test the startup procedures. Are they set up the best way? So what we saw in one project we had was that we could reduce 40 days of downtime because the startup procedures and the test sequences were tested and verified in advance before commissioning. So then again, saving even more days. And later on, when you have saved all this time, then the simulator again can be used for even more optimization. And what about upgrades? Normally at upgrades or control system or doing changes, it can be delays because the upgrade is not actually as successful as expected. And then the simulator could be used for testing the upgrade. And then avoiding 2 to 3 days of downtime because of unplanned events occurring, because the upgrade wasn't as good as expected. What we also see is that there's a possibility to combine these simulators or digital twins with online data from the plant. And then the next step is to look at that, how to update the control system so on the simulator so it is aligned with the real plant states, and also to look at what we can do there with these new states, and if we could look at what could happen in the future. So this is my last slide. So what a little bit recap. So and also what about the future? So historically, there was one operator training simulator it was focused on, also sometimes used for engineering and testing, a lot of high fidelity. Now we have more tools that we can combine, and also we can have real-time updates, and we are also more looking into KPIs and how to improve the value chain, and remote operation and remote rooms for operators, so we can train them so that they are more fit to meet that challenge, how to cooperate in teams and so on. And then we have prepared that by doing really, really good testing of the control system before coming to this phase. And what we see for the future is that there will be more and more focus on enterprise and prediction and machine learning, combining data, and seeing that more and more systems will exchange data, and we will get even more information out of that. So there will be big things also for the future that will happen, and we will be there. So thank you very much.
Sicherlich kennen auch Sie die Situation.
You certainly know this situation. Once your plant is being operated, new data is permanently generated and existing data is modified. To be more precise, your entire plant as well as equipment is documented in the form of data. Everything you have to know about your plant, everything that really matters, is spread all over numerous software applications, databases, and paper-based files. This means this data and information can neither be accessed easily or quickly, nor does it have any useful correlation. We call this data dark data. Let's be frank. Can you actually rely on this data? What really matters is how the data can be managed efficiently across different disciplines and along the entire life cycle in order to provide relevant information for substantial decision-making processes.
Und hier kommt Planzeit ins Spiel. Planzeit wurde speziell für die Prozesse.
Here, PlantSight comes in. PlantSight has been developed in particular for the process industry and consolidates all information and data, be it static or dynamic. You can consolidate, contextualize, validate, and even visualize your data and information with PlantSight. The raw data is then transferred to a complete digital twin.
Ein lebendiges Abbild Ihrer Anlage.
It is a genuine copy of your plant, which is being updated on a regular basis and grants valuable insights. Suddenly, you realize new correlations and understand how everything is interconnected with each other, where to go further, and how you can actually work with the data right now. It doesn't matter whether you are an operations manager, site manager, engineer, or operator. PlantSight helps you reveal yet hidden data, make decisions faster, and thus increase the profitability of your plant immediately as well as on a long-term basis. All this is possible with only one simple web portal, which can be easily accessed. A completely new portal allowing for realizing and enhancing the added value of the digital twin along the entire asset lifecycle in process industries. Anytime, anywhere.
Jederzeit und von überall.
Siemens. Ingenuity for life.
Welcome to Siemens Session, where we will be addressing the value of a digital asset portal in your daily operations. Your presenters, Nigel Sams and Gert de Nul, will take you through this session, which will incorporate an introduction and live demonstration. Under the topic of digitalization, all companies are looking to take advantage in this transformational change and new ways of working. All companies, all sizes, any locations. This fourth industrial revolution is bringing values to every company. By providing new business models, helping to achieve better efficiencies, improve cost and schedules, maintaining and improving quality, whilst also taking care of important issues such as health, safety, and the environment. If we look at the digital transformation within process industry, areas to take advantage here are big data and Internet of Things, cloud and edge technology, and incorporating information retrieved from analytics and made beneficial through artificial intelligence. On the right-hand side here, we can see that approximately 60% of potential benefits can be found in these three areas: day-to-day operations, reduction in cost, and improvements in health, safety, and environment. We shouldn't ignore the other areas. There are still huge benefits to be found by making improvements to the way that we operate plants and our environmental footprint. Siemens has been involved in these transitions from one industrial revolution to another, starting from electrification, then progressing through automation, and now digitalization, which we are calling the fourth industrial revolution, Industry 4.0.
Siemens is a large, very large company, but we have a division, industry software, within the company, which is actually in the top 10 software companies in the world, with recognition as being number one market share, having almost 25,000 personnel in software development, and over 5 billion euros in R&D expenditures yearly. Let's get on to the challenges for the industry in managing plant data. One big challenge is to ensure that when you make this digitalization transformation, it is in keeping the virtual environment in keeping with the real environment as it evolves over time. Today, engineering data is found in various disconnected sources, so the benefit of having everything in one place is a desirable, and it will bring real value in the aim to find these benefits of cost, time, and savings. The virtual world here allows the collaborative effort of across plant operations, all stakeholders, whether it is the installation manager or down to the inspector and the process engineer who spend some time on the plant. Again, the importance of keeping these two closely connected so that as the real world evolves, so all of the data is brought into the immersive environment for those benefits. Siemens, in collaboration with its strategic partner Bentley Systems, has developed a solution which we brand as PlantSight, and Siemens has identified 6 business areas where PlantSight can bring great benefits. If we look at the view on the left-hand side here, this is the DNA of the plant. This is the information, the engineering information which has been created from the early phases through conceptual design, detail engineering, to be able to construct, build, and hand over the facility. On the right-hand side, we can see the real-time information which is collected, and it represents, you could say, the pulse and the heartbeat of the asset. So bringing these two together to see how my plant is operating compared to how it was designed to operate is critically important and will provide those meaningful insights for any decisions which need to be made. An example could be a critical piece of equipment which is scheduled for maintenance, but by looking at the information, there may be a potential of postponing maintenance if it really doesn't look like it needs it, or inversely, bringing forward maintenance if we can see that there could be a point of failure before the next planned campaign. Today, in this session, we're going to address the digital asset portal. The digital asset portal is an information-centric solution to provide a digital twin accessing information across the entire life cycle. It's a single source of truth of that 1D, 2D, and 3D data, providing real-time operational data and everything in context. The capabilities, as I've said earlier, it is one portal to access all information, bringing together the static engineering, the static content, providing insights for all of those disciplines, whether it is a KPI to the installation manager, or whether it is information to reliability engineers, maintenance, and inspectors. And benefits here are efficiency improvements, reducing time, and faster reaction to making better decisions with better information. This is an early look at a digital asset portal environment, and I'm soon going to hand over to my colleague who will provide a demonstration of this. Typically looking at the failure mode event analysis to see what could be the real problem and therefore shorten the amount of time for maintenance and inspection remedial work. So at this point, I'd like to hand over to my colleague, Gert de Nul, to take us through the demonstration.
Thank you, Nigel. So now we'll start with the demonstration part of PlanSight as a digital asset portal. And just to show here what we are going to demonstrate is we have several people, disciplines in the facility. And so I will show how PlanSight can help in coordinating the communication between the people in the field. So between the reliability personnel, production personnel, inspection and maintenance. We will start our demonstration. There has been some alarms triggered in the plant due to a failure or some cause on a pump. And the production personnel is going to send out a notification to the reliability center. So they can then have a look and try to find the cause of the issue and take some measurements. So we'll start our demonstration as me as a team member of the reliability center. So now I come back from lunch as a member of the reliability team, and I see there is a ticket raised to me and assigned to me related to an oil level indicator dropping. From this open issue, I can click on my ticket, and now I see some additional details about the cause. So we have here oil level indicator dropping, causing alarms. And I already have an indication that's related to a tag P05201. And the production personnel gave me the description that there are frequent alarms he's receiving, and he's requesting me to investigate for the cause. They, in production, they did not take any actions here. They just are requesting some feedback, at least within 2 days. So on the right side, I see that there are no any links or information assigned yet to this ticket, so that we can fill up according how we are resolving the issue. But from productions, they already assigned a link to the manual of a water pump related to this equipment. So this I could already open and look at the manual. On the bottom left, I have a link, and when I click on this link, this will bring me to the visualization of PlanSight. And because I don't have immediately a clue what type of pump it is, or the size of the pump, or how it's related in the 3D environment, with the visualization, we can see here now that this ticket has been assigned to this pump, and I see maybe it's a horizontal pump. It's not a very complicated one. And the system itself is also fairly simple. We have a column with some 3 pumps in this system. And here I could already decide already a bit, okay, if it would be maybe a complex system that I maybe would need to go on site, or if I could call somebody to give a quick hand, and he could be my eyes and ears to have a look and check out this pump for leakages or something. But I would like to investigate more about really the root cause here in this case, about our oil level drop. So I'll switch to the dashboard solution of PlanSight. PlanSight dashboard solution gives us a complete overview of our system here. On the top left, we really see the diagram of the process, schematic, and overlaid with real-time data. So this can come from the DCS or any historian from the facility. On the bottom, we have some critical equipments and their health status. So they all need probably some attention. As we see here, a lot of them are in orange or in red color coded. And our pump P05201 is also in this list. There is definitely not an issue here. On the bottom right, we have recommendations that can come from people on the field that hear some noise or strange behaviors on equipment or in the system, and they can give recommendations on the plant side. That could also be driven by some analytics that maybe give recommendations how to improve the performance of some items. But I'm more interested on the top right side, where we have all our critical equipments classified and rolled up by health. And it also gives an indication if the machines are really running within their limits of safe and reliable operating conditions by means of KPIs of the integrity operating window that we see here in these columns. There is definitely a notification on our pumps here, and we see that the health is really low. So there is definitely an issue with our pumps in this system. So when I click on the pump icon, it brings me to a complete list and overview of all the pumps in our facility. And we can here already do also comparisons, for example, between same pumps from the same manufacturer to see if they are all running in their limits and have the proper health as expected. But now I would like to go more and dive deeper into our detail for our P05201. And again, I will click, and that brings me now to an operational view of our specific pump at hand. From the previous screen, you also saw there were recommendations. You see here again recommendations. And recommendations are always visualized in context of the dashboard. So we drilled in, we have a holistic view here of our plant side dashboard. So we went from the system level up to the pumps, and then now we are in the detailed view of our pump. And so now we have contextualized information as well in the recommendations for this pump. From the alarms and alerts list, we see there is indeed a fault reported for the low oil level. Don't see immediately problems related to the actual process values, production values of the pump. They are really running as they are designed. But the efficiency is quite low, that you can already see here. I will go now to the reliability tab, just to have a look if there are no faulty sensors that could cause maybe this alarms from the low oil level. And at first glance, there are indeed also no fault signals or sensors. What I can see is that there is a mean time between repairs that is quite low. So that's something I will maybe investigate further after we look at the cause for a low oil level drop, because that is definitely not a good metric here. I already start to suspect we'll have to do some inspections for this low oil level. And so I can set up now also a call with an inspection colleague to find some strategies or actions to do for the inspections. So we can use, for example, Teams or a Skype, some remote collaboration tool. And I will give him a call, and together we'll go now to the engineering tab, where we have access to the failure modes of our pump. Failure modes and effect analysis of FMEA provides us some information. What are all possible failure modes could happen on this pump. And they each provide, when we click and highlight one, they provide what are the countermeasures we can take, what are the effects, and what are any strategies we could take to resolve the issue, and as well with the recommended actions. So together with our inspection engineer, we can now go and find what are could be the causes of the low oil level drop. And for example, there could be pump oil seal worn, and then we can see we need to do some visual inspection for the seal wear. And so we can, together with the inspection, we define really now the proper strategy and inspection measures he has to take. If we want to know a bit more in detail how our pump is related to the full process, and this will open the document management system and opens the PNID, interactive PNID from the document management system, which will then highlight on our pump symbol. And now we can reflect on how this pump is in relation to the other parts of the system. As we can see, there is also a backup pump and so on. If we had a CCTV in our facility, that could also be visualized here. So we could then do some remote inspection just to see if there are no oil leaks on the ground from the CCTV footage. But unfortunately, in this demonstration, we don't have a real physical CCTV hooked up to a real facility here. But that would be a possibility to enhance. We can also have a look to the maintenance, because maybe your inspection engineer said, yeah, I did some maintenance in the past. So maybe let's have a look to what happened in the past related to maintenance. So we see there is already an open ticket to inspect for check and the grease wear. But if you look at the closed tickets, we have now access to the work orders that happened in the past. So, for example, we are suspecting that could be again a seal worn. As we see here, there are some pump wear check, a standard pump wear check and grease happened. And so using the work order ID, we could now look up also the details of these work packages. And that could give us some more insights. What could we expect as probably what would happen from the inspection results that could suspect that there's already maybe again some seal repair needs to be happened. From this work order details, we can then also have a look to the spare parts that were used in this maintenance activity. And we could already be proactive and just reflect if there's already the necessary spare parts or they are not running out of stock. So we could already then, for example, say we need some additional seals or bolts, and then we could make a request to the supply chain. So I will go back now to my ticket. We have identified some strategies, some visualization checks that my inspection colleague will have to do. So I will go back now to my ticket, where I will sign this now off to my inspection colleague. So I will open the details of the ticket. Now I can make just some comments. So urgent inspection needed. Relating to this request from production. And we will just, as a reminder for him, visually check and around the pump for oil leakage and report any other abnormal findings, noise, vibration, as discussed. So this is just a reminder related to this request. Okay. So this is just a reminder for my colleague of the actions he has to take that we discussed together in the dashboard solution of PlanSite. And now I can assign that to my colleague, and I will use for this my alter ego, which is me as inspection engineer. So now I can save this and go to this ticket will now be sent to the inspection engineer, and he will receive that now also as an email with a link. So he can immediately open it up in PlanSite and drive this issue ticket now further. With his mobile device, he could, for example, during the inspection and checking for oil leakage, if he finds any findings or leakage, he can take pictures, attach it to this ticket, or if he finds any wear on the pump that could cause any of these oil level drops, he could also open up the link in the visualization tool and then mark it up just the exact locations, for example, where to assign, where he found the wear and tear on the pump, or where he found the leakage on the ground, because maybe it could be, for example, also from an oil leakage on the piping or so on. So he could really mark it up and hotspot it in the 3D environment, which would help then also on maintenance to understand better the context of the problem. Okay, so now the ticket has been sent to the inspection engineer, and then later on, once he has done the inspection, the same ticket with all the audit trail will go probably up to maintenance and so forth. This was the demonstration part of PlanSite as a digital asset portal.
Just to wrap up the session with some key takeaways. So we can see that a plant digital twin will provide that representation of the physical asset or process or system. It's critically important to keep it continuously up to date as changes occur on the real plant. And the ability to generate insights enabling that reliability engineer to decide the probability and likelihood of the type of failure mode, understanding the effect and the consequence of this in order to engage maintenance where required. Here are the different stakeholders in a collaborative environment, and the ability to drill down to finite information, to look at past work orders, to understand the history of the asset, of the system, of the plant. That's the end of this session. Please reach out and contact us. We'll be on our booth, and we're ready to talk to you about the PlanSite Digital Asset Portal.
Welcome to Kongsberg Digital. Today I will present together with Roar Nilsen what we do in Kongsberg Digital. First, Kongsberg Digital is part of Kongsberg Group, which is a technology powerhouse with 3 strong business areas. It's Kongsberg Maritime, it's Kongsberg Digital, and it's Kongsberg Defense and Aerospace. Our 3 business areas all delivers excellence in the markets, and yet we are one company, one Kongsberg. We work together as one team, translating innovations from one business area to the others. Our common denominator is our technology core. Our strong competence and capabilities transcends business areas, reaching across the entire company. This makes us among the best in our fields, able to deliver extreme performances for extreme conditions. Several of our state-of-the-art solutions and the results are the results of cross-company efforts and achievements. And we are not going to curb our ambition. We will continue utilizing the combined muscle to deliver world-leading technology, systems, and solutions. So, first off, what is a digital twin? A digital twin is a virtual representation of the physical elements of an asset and its dynamic behavior over its life cycle. Kongsberg Digital Twin Service Platform, KONGSBERG, is a portfolio of services helping energy asset operators to establish such digital twins of their facilities and fields. The components of a dynamic digital twin. What is required? Digital twins in their simplest form visualize assets and processes in 3D and 2D. Adding asset data enables a single source for asset information, promoting efficiency and collaboration. Adding real-time data and with high-fidelity physics models improves data quality and provides live performance insights. Combining data-driven models with physics-based simulation improves data quality, accuracy, and unlocks improved performance in real time. Over time, this drives towards greater performance, automation of complex decisions, and higher degrees of autonomy. With the availability of cloud and scalable infrastructure, we have leveraged our digitalization expertise to build digital twins to drive collaboration and facility performance. Our observation is that digital twins are now becoming more of a standard, and it remains high up on the to-do list across the industry. The direction is clear. Operators want a framework to digitalize the management of assets. They want to drive collaboration, improve decision-making, optimize resource utilization, and focus on efficiency. Our digital twin, KONGSBERG Energy, integrates with your information architecture and provides a complete view of your assets and their dynamic behavior. The platform can be rapidly deployed to improve collaboration and becomes a cost-efficient vehicle for digitalization. This helps operators within a range of topics such as simulation and flow assurance, production optimization, collaboration, condition monitoring, asset integrity, and integrated planning of work. This is a picture of the overall architecture. It's from the bottom, you can see the different data sources that comes into the platform. Everything from subsurface data to real-time data, different type of source models, asset data, and business data. All these are enabled through data integration into the platform. We also have a contextualization engine, and we have a model engine, and everything is available from the Twin Service API at the top. Important part of the contextualization engine is how quickly it brings value. We call this the KONGSBERG Unify, which unlocks the value of your data. And by quickly, this can be as little as 8 to 10 weeks. Engineers in the energy industry is used to working with a variety of data, from time series to piping and instrumentation diagrams, through pin IDs to 3D and 2D models, simulated data, and so on. Challenges like having a massive amount of data that is not connected, data silos, data is stored in different systems, data quality issues with outdated and incorrect data, and lack of productivity. Personnel spend most of their time manually collecting data and combining it from different sources. It's difficulty to get useful insights from data to improve the asset performance. To achieve the full potential from engineering data and get an efficient overview, new ways of contextualization are needed, and that's where the CogniTwin Energy Unify engine comes in. It ties all the data, structure, and semantics together without necessarily needing any master model, and it utilizes algorithms and artificial intelligence such as machine learning and acts as the glue that links the various objects from different sources together. So it's an important part of the technology platform. It brings data together from siloed enterprise systems and data sources, as shown on the previous page, and shortens the time searching for and structuring information. All of this has actually resulted in that we were awarded a major contract by Shell for the deployment of the dynamic digital twin of the Nyhamna gas processing plant in Norway. Then in 2020, Shell awarded KDI, Kongsberg Digital, with an enterprise agreement for deployment of digital twins. The agreement covers digital twin cloud-based services for the global portfolio of assets and capital projects within Shell's upstream, integrated gas, downstream, and manufacturing business lines. As you can see here from Yuri, Chief Technical Officer in Shell, our collaboration with Kongsberg Digital in developing digital twins in a new era of visually interacting with data and models at the asset, equipment, and component level. Digital twins drive efficiency by enabling remote operations, automation, and significantly improved collaboration. It supports our frontline operations to better leverage insights from big data, transforming ways of working to unlock value and increases resilience in the changing business environment. Let us now turn the focus to how some of our customers use the twin in daily operations of their facility. First, we will cover collaboration, which is features enabling shared situational understanding and collaboration across teams, disciplines, locations, in addition to workflows supporting common operational processes. Then we will highlight optimization, which Roar will be talking more about here today, which is workflows and features powered by on-demand and always-on models. First, operator value and usability. The Collaborate features provides operators with a common browser-based surface for enterprise collaboration and problem solving, including live enriched PIN IDs and infograph with rich user access to time series data, events as they become available, and engineering data at your fingertips. It enables significant worker productivity as documents and data is contextualized and easily available for use. One of the ways the Collaborate features have been implemented with a client is in the maintenance work planning process. To quote a mechanical discipline engineer in operations, the digital twin provides a more efficient and safer work preparation process. Easier communication across teams and disciplines, reduction of meetings, faster way to locate equipment in heights, less data cross-checks between applications, and less logistics and time spent on field inspections. We can now both communicate and make decisions on the exact same and unified data foundation. So, how does it look like and how do they benefit? Unfortunately, we are not able to show a live demo here today, but this is a 3D view taken from the Nyhamna gas plant, where we have a digital twin for Shell. From bird's eye view of the plant down to every equipment detail, they can navigate, measure distances, locate and enable equipment layers, and plan their work packs. With navigation in this close to real plant 3D environment, the work planners reduce the amount of site visits needed. And as mentioned, any modern device, tablet edge with an up-to-date web browser will be sufficiently able to run this web application. The planning of preventive and corrective maintenance requires daily collaboration in multiple systems, such as SAP. With the digital twin, the multidisciplinary planning teams can explore and navigate to the documentation and drawings and a rich 3D model. In this slide, we have opened the piping and instrumentation diagram, PIN ID, on the right side. We have also highlighted the whole PIN ID equipment in blue in a 3D model for easier visualization. Here you can choose whatever color or filtering you like. The work planners can move freely between the PIN ID and 3D model in this split screen setup. In the order they like, they can navigate to an object in 3D, find it in any of their PIN IDs, through a search or any other of the linked documents they have available. They can shift between 2D and 3D functionality as they wish. They can also isolate any component for easier overview, since these facilities tend to be quite crowded with piping and structures. On the left-hand side, we can see the 3D view where we now have selected and zoomed in on a suction scrubber. With a click, we open the Infograph Explorer in a split screen, which utilizes the KONGSBERG Unify I mentioned. Here it shows all the linked data from a variety of different sources and the relationships together. Related tags, connection to 3D model, work orders, documents, drawings, images, and so forth. The work planners no longer need to spend time pulling drawings from the different places to compare, distribute, and analyze, which improves communication and decision making. No more searching around in different data silos trying to find and link information. This picture just shows an example of the internals from an inspection job of the selected suction scrubber. With a quick tag search or a click on a 3D object, all relevant pictures can be accessible, both historical and the most recent ones. This is quite valuable, as libraries of pictures tend to be stored in different folders owned by multiple teams and disciplines. As work planning is focused on maintenance to be scheduled weeks, months, and years ahead, the work planners are also able to look up their transactional operations data from any tag search, such as notifications of equipment error a field operator entered maybe on a night shift, work orders the planners have in their portfolio for the next 6 months, and work permits for the maintenance execution. And for more even detailed planning, the work planners are able to view real-time data and trends to understand the behavior of the equipment they have in scope. Open in their browser at once, they have quite a good overview with both the drawings, 3D view, and trends, easily available for everyone. Another way Collaborate provides asset insights for daily decision support is through the workflow simultaneous operations. From a shift supervisor in operations, we have this quote: "The digital twin gives an effective situational awareness of critical and non-critical activities and helps us evaluate, prioritize, and approve work for simultaneous execution. It is now easier to identify situations that could compromise safe operating limits and stop activities that cannot be done at the same time." With the workflow for simultaneous operations in digital twin, site personnel have an effective visual of the work permits, technical deviations, work orders, and notifications. This provides a cumulative risk picture of the operational barriers and assists in daily evaluations of approving concurrent activity execution. In example, is it okay to perform scaffolding work in heights nearby this other job, as an example? Can we allow for work with active ignition sources, this close to a work on a system with hydrocarbons? Where are potential conflicts or increased risk, and what mitigations or controls need to be considered? An important part of barrier management against undesirable events. In this twin view, the various work permits for a given day in a given area of the plant are visualized in the 3D model on the respective equipment tags. To the left, a list of relevant information for the work permits are listed. Here, filtering options are available if they need to focus attention on work to be performed by one discipline. In one system, one type of work groups such as lifting, pressure testing, special transport, digging, and so forth. For a selected time period and a chosen set of operational data like work permits, work orders, notifications, or technical deviations, maintenance crews, planners, and shift supervisors are better equipped for their risk evaluations, and they can make data-driven decisions in a completely different way than before. Here you can see for example, as an example, you can open a work permit and have also direct access to SAP data. Lastly, another example is the corrosion under installation application, or CUI. Another quote from an inspection engineer in operations: "The digital twin provides us benefits like more effective planning and execution, improved condition oversight, and improved degradation prediction. This leads to a more effective and targeted inspection program." Corrosion under insulation is a type of corrosion which arises when water becomes trapped between insulation and the piping and vessels it is designed to protect. This has contributed to more than 20% of all major oil and gas accidents in the EU alone over the past 35 years. In other words, CUI is a major safety challenge and the single most expensive corrosion issue in the oil and gas and petrochemical industries. The goal is to predict where corrosion during installation is expected to occur through the use of process data, maintenance data, and geometry data, along with inspection results. So, how can digital twin and data-driven operations help? Well, by linking inspection results to tag data in existing data sources and using 3D visualization, the most important parameters for predicting COI can be identified. The Twin can also let you add virtual sensors such as temperature edge around the facility for increased understanding of the most critical corrosion parameters. In this view, the inspection engineers can view inspections per corrosion loop, filter on status such as cladding, and view any details. The integration between the results in the inspection database, all design data, and live process data will give valuable insight in the COI degradation mechanism. This in turn should improve accuracy in inspection point selection and condition prediction. In total, this can be used to predict corrosion on installation, COI, resulting in an optimized inspection program with reduced operating cost and risk over the asset lifetime.
So this is another quote from one of our users, process engineer in operations. The dynamic digital twin allows us to explore the operating envelope, both under stable operation and in transient between one operation scenario to the next. This opens up for a completely new way of performing optimization, where the ultimate objective is to maximize production and minimize energy consumption, while reducing maintenance and avoid breakdown of equipment. So for the asset of Nyhamna, we implemented, this is how we implemented the modeling, the always-on models that also Stian Tangen said something about for the match case-wise match solution. So the always-on models are driven from operator commands from the field through a Cognify Edge gateway. Take that into the Cognitwin environment and push all the operator actions into the model. The model is now synchronized in real time with the same condition as in the plant. So when the operator is opening a valve or starting a pump here in the field, the same will happen with the always-on model. So in that way, we can now compare the sensor readings from the models and the calculations from the models and the sensor readings from the field. So here we can then see when equipment starting to drift and if they have problems with performance of the equipment. So up here you will see that all the data is enriched on top of PNIDs and system control diagrams and 3D models, and it's also available through portable mobile devices like iPhones and tablets, and also used in the integrated operations center. So from here we are also able to have multiple versions of the same model running in parallel, looking for the optimized condition. And we can now also take one of the cases and bring forward to an what-if scenario. So in a what-if scenario, that can be where you can actually run multiple versions of the modeling behavior to search for a better way of operation or an alternative solution to the operating condition that you have today. So all this is available through the web interface and easily available for the entire organization. So what we are doing together with these physics-based models that Stian showed earlier today with KSPICE and LedaFlow, or any third-party physics-based models. We also combine that together with data-driven models, so which will be a hybrid modeling approach. And we run all this in a safe condition with the engineering data and cyber security in our platform, and can easily give all the domain experts access to the data in real time. So the data-driven models are now not only trained on the real-time data, but also data from the physics-based models. So here we can actually build on the strongest capability of both worlds. For the physics-based models, that is, of course, more accurate and more robust on the dynamic behavior, and the data-driven models are much faster than the physics-based. So when we combine those two together, we get the best out of two worlds. So in this application, this is one of the applications that we have built for one of the assets, where we're searching for the optimum power consumption for a particular flow rate. And here you see that we have different cases running in parallel, validating results from the machine learning model, the data-driven model. So the data-driven model will then propose new settings in the production, and we validate that through dynamic models, just to test out if this is actually if the plant are capable of running with that type of settings. So then it's all validated through physics-based models before it is recommended operations to the operational team in the controls room. So here they can optimize on the pressure or the number of compressors running, how many compressors they are running upstream here, or how many export compressors they are running at. And it's all dynamic because the back pressure in the pipeline, the export pipeline here, is changing all the time, so that is not stable, and the different flow rates from the different fields coming in is not stable. So then it's all changing, and it can all be optimized to reduce the total power consumption and to maintain the production, of course. So just to summarize what we have talked about now for the dynamic digital twin, we recommend to start with the collaborate function. That is actually integrating all the data from the asset, the all as-built data, the design data with 3D models, 2D models, and stitch that together with documents and available spare parts and all that, which we call the collaborate functionality. That gives the whole organization access to data in real time, and also, and not only that, of course, it's also give them also the operational data, the work order, the work permits, and what Håvard mentioned. So all this, building that in context, gives the whole organization access to the single source of truth. And that builds a lot of efficiency gains for the processes. Yeah, what we have heard is between 30 and 70% efficiency gain is for the maintenance, collaboration, and planning and execution. And having this in place first, and then moving over to the more advanced section with the dynamic optimization in the process, using both physics-based and data-driven models in a hybrid modeling approach. That gives us the capability of reducing the operational the OPEX with 1 to 10%, and also increase the potential of increasing production when you have that possibility. For this, for the plant that we have looked at, that is only reducing the production of the power consumptions, because they are going to deliver what they are designed to deliver, or not designed, but told to deliver. So they have a daily nominated production rate that is going to be delivered as efficient as possible. So that concludes the talk for us today. So please contact Håvard or myself to discuss how to implement a solution like this, and how we can help you to build on the data that you have. Of course, again, it's important that you don't need everything to start. You can start with what you have, and we build on that and further improve your digitalization journey. So that brings you into the optimization cases as well. Thanks.
let's start with our discussion. I think that this topic is especially interesting these days, as all our usual problems are even more highlighted. And all of us, both on personal and professional level, need to accept a new set of technology skills. And actually, I wanted to avoid starting with this topic, as we are all full of it. But yeah, what could be more into question about technology meeting the human factors than this COVID crisis we are all facing? So we are coming from different parts of the world, and we have different circumstances. So I would really love to hear in short from all of you, how did it influence your training strategies and everything, you know, besides mamas, papas, grandparents, and your dog learning to use Zoom? How did it influence control rooms, operators, and what good can you take from this crisis for your future business? So let's start with Yari, shall we? Yari, what is going on in your company?
Thank you. See, VTT Technical Research Center of Finland is a research organization, and we are developing these training simulators together with the Finnish nuclear power companies. So perhaps the main influence has been to our possibility to carry out our research in these training simulators in Finnish nuclear power plants. But we have had opportunities to carry some of our experiments, for example, last year. But it has also promoted some developments. For example, we have developed so-called virtual reality control room, in which these operators are able to operate power process in a virtual environment, and this virtual control room is based on the APROS simulator model, so that it's a full scope simulator in this respect, that you are able to carry out all operators there. And basically, it's possible that in the future, operators can sit at home on their sofa, and basically it's possible to even operate the control room there. It's possible in our this kind of virtual control room, and we have developed new kinds of these kind of virtual headsets, in which are based on a new technology that has been developed in a Finnish company, Vario. And for example, because the resolution has been a big problem in this virtual control room, operators are able to operate their panels as in a physical control room, but it's very difficult to, for example, see on their workstation what for example from a distance, for example, what is presented on a large screen display, or panels farther away from the workstation. So this has been a real problem, and this new technology provides new opportunities to improve the resolution of the virtual environment. So
very well. So you are using this crisis to benefit from even
exactly.
Performing more research.
That's right. Yes.
Yeah. That's fantastic. And Peter, how is going on in Germany inside your company? How are you dealing with the crisis?
Well, that depends on which branch of the portfolio you are looking. As you said, we are a training service provider for the German and one Dutch nuclear power plant. And we in Germany have a decentralized training aspect. So every training is done at our site in Essen, and the trainees from the nuclear power plants are coming to us. And with the travel restrictions that we are currently having in Germany, this is of course impacting us very much. For example, we needed to adapt trainings for our Dutch customer who were not allowed to come to us anymore. So we used the audio-video system of our full scope simulator to transfer the signals into the Netherlands. That worked out quite well. Of course, we are also a simulator vendor, and for the projects that we're heading, especially for conventional power plants where you have screen-based simulators, all the testing has been done remotely. Because we have an Austrian customer that was also not possible to come to us anymore. So we used this as a chance to improve our remote testing technologies and conducted all the simulator testing remotely, which was very successful, I would say. And if you're looking for the theoretical training classes that we are doing, we switched all the trainings into virtual classrooms. So we're also conducting training for a Swiss customer in virtual classrooms where we set up a whole studio where the trainers could do the training and use all these new conference tools to conduct the trainings. So also for us, we used this pandemic to improve our technology set on how we conduct the trainings.
Yeah, and I believe from what I hear from you that many of these positive effects will be here to stay. I mean, improved communication and remote work.
Yeah, exactly. To me, I think that with how we changed the way to communicate in the pandemic, that is something that we will prevail for the future also. There will be less traveling. We will use these tools much, much more as we did in the past. And it is a good chance to set up the technology that we need to have in the future and to adapt it to the trainings that we conduct on that new technology. Because the whole world is using it for different aspects, so we can also do that for training aspects.
Yeah, perfect. Cash, how are things in EDF Energy? How are you dealing? What are your new technologies that are improving?
Well, we have used video conferencing facilities to carry out, for example, factory acceptance tests on simulated projects. Let's say when the vendor is in Canada and our engineers are on site, and of course people cannot physically travel across, we made use of video conferencing facilities to witness the testing that was going on remotely, and also have a set of hardware in the UK to carry out parallel sort testing. So technology was used in that sense. But in the UK, our main control room training simulators are on each nuclear power station site. So in the simulated control room, we have the hard desks and panels fully instrumented. So it's relatively easier for our operations engineers to come down to the simulated control room training facility and actually carry on testing as they would normally using the hard panels and desks and panels and switches and so on. Of course, the instructor is usually in a separate room in his tutor booth area, whereby he is able to look down on the trainees in the simulated control room and observe that they are carrying out their task properly, using either physically looking through the window or listening into microphones that are that the operations engineers are wearing, or microphones that are on the hard desks and panels at various discrete places, and also making use of cameras that record what's going on in the simulated control room. So in that sense, we have been able to, because of social distancing, etc., carry on physical training on each nuclear power station site, and also make use of video conferencing facilities to carry out remote witnessing of factory acceptance tests. And we actually, for on one of our simulators, we when we were due to have site acceptance tests, we actually had to get our simulator vendor and to send over an engineer all the way from Canada to the UK to our nuclear power station site and carry out COVID testing before he flew, before he got to, and then he was constrained to his hotel for a couple of days, and the COVID testing was done again, and then he came onto our nuclear power station site to carry out the site acceptance tests, etc. And then he was regularly tested whilst he was there. So there are workarounds and solutions to the present COVID pandemic problems.
Yeah, we are also focused on problem solving now, and at the end, very good to hear how many benefits it brings for future business. Ricardo, so your company is based in Japan. How are things moving there and influence on your overall business in Europe?
Okay, let me let me make a correction. My company is not based in Japan. My company is based in Wilmington, North Carolina. Okay.
Okay.
GE Hitachi is a global company. It's the result of a joint venture between General Electric and Hitachi. Okay. This joint venture was created to combine our nuclear pedigree with Hitachi experience on modular construction when talking about new generation of reactors. Okay, so this made our option very exclusive. Okay, so like I was explaining to you, I'm working in a global company. So one of the main challenges for us is being able to have all the different level of details of COVID protocols on all the different countries where we are working. Because at the end of the day, you know, we are dealing with outages, we are dealing with services, and you know, today we are working in US, tomorrow in Finland, the day after we are working in Japan. So at the end of the day, you know, each country is having its own COVID protocols, etc. So this is the first challenge that we are facing, being able to put everything together in order to being able to cover all our workloads with the same personnel we have working for the company. Okay. So from remote working point of view, you can imagine working in a global company with people located in different continents is not a big change. I mean, we used to work a lot remotely. We used to use a lot of Teams and these kind of technologies for meetings and these kind of things. So from that point of view, this has not been a big change for my company. Okay. From training point of view, obviously, it has been a big challenge, okay? Because at the end of the day, you know, with the COVID protocols, you need to be able to reduce the number of people working together in order to avoid the spread the virus, etc. So basically, my company have had to reduce at maximum the presential training and just do it in cases where was really need, okay? Moving on simulators, the simulators we are putting together based on the feedback I was listening to my colleagues is a little bit a different concept. Okay, so basically what we are doing in our let's say first of a kind simulator is use a completely new yes patent virtual reality technology that is allowing us to fully replicate to the last level of detail the power plant, but is permitting us also to have multiple players working together, simulating the real procedure or the real process. Okay, one example, a fuel movement simulator that we have just patent and developed. Okay, so basically it's permitting to us to exactly have the people exactly replicating the fuel movement process in a boiling water reactor. What is also new related to this technology? That, you know, we are not the necessity to do it in a certain location. I mean, we have the possibility, for example, to have the coach working in US, in our headquarters in Wilmington, North Carolina, and the customer working on his site, because we have been able to develop a deployable virtual reality concept, okay, that is able to be transported to wherever in the world, is able to put together in something around 6 to 8 hours, and is able to connect using internet with other locations in order to permit individuals that are in different physical locations work together in the virtual reality. Okay, so you can imagine that, you know, this is a very good asset in the actual condition we are living, because at the end of the day, you know, it's going to permit to you to avoid a lot of travel. It's going to permit to you to be much more cost effective. I think everybody in the call is aware of the relevancy of the training in the nuclear industry. Okay, historically, this training has been linked to very cost physical mockups with very high maintenance cost, with a lot of different investments needed to have this, let's say, active. Okay, and this is what we are trying to avoid with this new generation of virtual reality simulators that is putting in front of us a lot of different challenges. Okay.
Yeah, Ricardo, thank you for explaining and also correcting me. You opened a very good topic that I wanted to continue discussing with you. So in innovation and all of these patents that are happening, improving your technology, improving your business strategies, they are all fantastic, and people in your company gave a lot of effort to do it. But you know, when innovation, the bigger innovation is, it can sometimes come to bad like effects in how you apply it with the client, with the customer. So how do you manage to pass over these human responses that are not always ready to accept new innovations, new things, because it pushes them out of their comfort zone? How do you deal with this? And what is your experience?
This is a very good question. More if you consider that nuclear industry used to be a kind of a skeptic when talking about digital things, because, you know, there is a perception that could be a risk from cybersecurity and these kind of things. Okay, so I agree with you that it was not easy to get it introduced. Okay, so basically what I did was, do different attempts with different strategies in order to detect which was the better way to have the customer recognizing the value. Okay, my first attempt, and I was lucky because my first effort was internally into my company in order to get my company supporting my idea, because, you know, the virtual reality innovation platform that we are developing in HITACHI has been created by me, okay, by me and my team in Europe. Okay, so I had the opportunity to, let's say, the selling process internally into my country, into my company. Okay, and what I learned is that, you know, I was able to spend hours and hours talking about technology because, you know, I'm very passionate about this virtual reality innovation platform. But at the end of the day, it was difficult to have the listener, was difficult to have the audience really understanding the size of the solution you were developing. Okay, so at this step was when I made a pivot into my strategy, and I decided to perhaps not spend too much time trying to explain what I was putting together and invest more time on have the customer moving to the facility to put their hands into the solution. And was perfect, because as soon as we have the customers, the first attempt we did was in 2019 in a Spanish Nuclear Society meeting that is concentrating all the Spanish nuclear industry. And we put together the deployable virtual reality room, and we have there all the different country chief nuclear officers and site managers, okay, even some people from the regulatory body, okay, and the response was amazing. As soon as they were putting their hands on the fuel movement simulator, as soon as they were able to move fuel virtually in a power plant, because you can imagine, very often the site vice president or the chief nuclear officer has no previous experience moving fuel. So this for them was a very amazing adventure, let's say. Okay, so, you know, at the end of all the different sessions, we were making questions to them. All of them were very surprised. All of them were really valuing the level of detail we were able to put together when we developed that fuel movement simulator. We have a very nice icebreaker, because, you know, the lady from the regulatory body, you know, in the middle of the movement was coming to us with a question, hey, what happened right now? She was having the fuel in the grapple, okay, suspended. So what happened if right now I'm pushing the button to open the grapple? Okay, so we were telling them, we were telling her, sorry, nothing is going to happen, because at the end of the day, you know, in the nuclear industry, we are applying safe design. So it's impossible to open the grapple, but you can try, because at the end of the day, the simulator is replicating all the logic. Okay, so it was funny because she was trying, she was pushing the button to open, and nothing occurred, but an alarm started to beep. Okay, so at that moment I said to her, hey, nothing happens. This is designed to be safe, but you are fired because everybody knows that you touch the incorrect button. Okay, so our experience as soon as the people is inside, our experience is that they are fully immersed in the event, fully immersed in the experience. Another good anecdote could be related to our field movement committee moving to Spain, because our partner from a technological point of view is Spanish. Okay, so our field movement committee moving from US to do the factory acceptance test, the proof of concept factory acceptance test. Okay, and you know, they were spending perhaps 3 hours moving fuel in the virtual reality site. Okay, so you know, at the end of the day, we need them finishing that, because you know, it was important to do a discussion at the end of the journey in order to be able to evaluate which things could need any potential modification or whatever, right? So it was very funny, because when I was moving to the virtual reality room asking them to end the experience, the response of one of the operators was, hey, no problem, I'm going to do, but please let me put the fuel safe. So he was so immersed, his brain was so immersed in the experience that he was acting exactly in the same way he was supposed to act in real life in the power plant.
Mm-hmm.
And that's of course important from the training perspective, because this transfer or training is very important factor, so that what we are training, where we are training, the same and how we are training should some way transfer to the real world. And if you behave in the virtual world similar way that you behave in a real world, we can say that this kind of virtual training is very beneficial, and as beneficial as training in the physical training simulator.
The way we behave in the virtual reality is exactly the same than in real world, because we are even working with our hands. We have made some physical replicas of the important components in order to get the operator exactly doing the same process than in the physical side. And the only difference is that he's following the evolution on the virtual reality. Okay, and we have discovered that this application is not only useful to train skills, but it's very useful also to train culture. Okay, and on that area we have developed, you know, for example, one pill, one solution to train on foreign material exclusion. Foreign material exclusion is very important from a nuclear power plant operation point of view, because at the end of the day, if you are introducing any strange object into the vessel, you are taking the risk of have to face a mid-cycle outage in the middle of the cycle that is very bad for customers. Okay, so we create a pill where we were introducing on purpose 10 foreign objects in the field movement bridge, and the operator need to look for them, need to search for each one of them. Okay, this was from a skills point of view, but from a cultural point of view, we introduce a point where the operator, once identified the foreign object, need to classify it from a risk point of view on how it could potentially affect the core. So this is creating culture, because when you work on site, when you have the opportunity to go to the refuel floor or to other part in a nuclear power plant, and you make a question to the operator about, hey, this is a foreign object, are you aware of how this could be affecting the core? You discover a lot of times that the idea, the concept they have in his mind about how an object can affect to the core performance is erroneous. They are giving much more relevancy to big objects that at the end of the day are not allowed, for example, to go into the fuel cooling system, versus a simple wire that is very small but is very dangerous, because you know it can be traveling inside the fuel, can be creating a leaker, and can be causing a mid-cycle outage. So we are very satisfied with our simulator.
Yeah, we can feel your excitement. Thanks for sharing this. I wanted to ask from user point of view. So my experience with training simulators is in oil and gas. So energy is different, but again, the training simulator needs to behave as the real plant. So I wonder, Cash, from the user point of view, how is acceptance of your personnel, your operators, your engineers of training simulators, and are they happy to do the work and education on them, or they feel some resistance toward it, don't trust it maybe? What is experience from your staff?
We have been modernizing our simulators, main control simulators, since about 1998 across the country. And we have gradually added in more and more functionality on what we call the second unit desk. In the UK, the main control room has typically Unit 1 desk and a Unit 2 desk in the same physical control room. And in the past, the Unit 2 desk was always like a dummy desk, but not really with any simulation behind it. Right? So the training was always like on Unit 1 desk, and as I said, we gradually added in more and more technology to provide more and more functionality onto the second unit desk. And that change in technology was generally welcome because it started to provide more functionality on the Unit 2 desk using soft panels or glass panels, as they call it in some countries. And on our latest modernization, we actually made the second unit desk fully functional in terms of hardware, with simulation models driving it behind, so that the main control room could act as like a whole nuclear power station with both units doing different things at different power levels, different problems, etc. So the improvements we've made in terms of technology and functionality have generally been quite welcomed, because we always got the end user involved in specification phases, and as I said, the increased in functionality, increased training, team working, etc. That has been welcomed over the years across the fleet. And what we also did was to start adding in a classroom simulator. So that had soft panels only, no hot desks at all, which was something different initially. But it has become used more and more, not for the formal and full training, which is still, the full and formal training is still on the hard desks and panels in the simulator main control room. But the classroom simulator is able to focus on particular events for like pre-sort of training sort of thing. And again, the classroom simulator functionality and scope has gradually grown over the years. So, for example, on one of our nuclear power stations, we now have a full functionality using soft panels in the classroom simulator, so that they're able to look across the whole sort of like control desk and see all the switches and alarms and functions as they would in the sort of like main control room. And that was that sort of functionality and change was welcomed by the operations engineers on the station. And we were also able to use the classroom simulator to provide training to non-operations personnel from the engineering sort of areas. So generally, people have been quite welcoming of the changes and features and functionality that new technology has brought about in the last 20 odd years.
Yeah.
Yeah, and it's interesting for how long you are using the simulator. Yeah. Great. Peter, I hear that in Germany for nuclear power plants and your training services there, you are in the process of some changes and adoptions. Can you tell me a little bit about this? And
yeah, in Germany, the situation is very special, especially for us who are doing nuclear training, because you all have heard about the German strategy of phasing out of nuclear until the end of next year. So our core business is actually vanishing. There's no need for nuclear training anymore in Germany. So we are using that as a chance to bring the skills that we learned in simulator training also to the conventional side and bring the nuclear perspective there. Because what Kash just said is very important about the fidelity of the simulations. And especially on the conventional side, when I talk to people, I expect that I see that sometimes they think, well, a simulator has a very low fidelity. I can use it as a basic training tool. And that is not very widespread in the conventional side. And this is where we are going to currently. to bring the high fidelity simulations that we used to do for the last 40 years also on the conventional side. And in the projects that we currently did, we saw how the acceptance for simulations grew with the conventional industry. At first, when we did the projects there, they didn't trust the simulation. But when they first realized that, hey, these simulations are actually replicating the plants and doing what the plant will do in real life, they started to accept that. And we found lots of issues on the simulator projects that were still persistent in the plants, in the digital control system, and also thermodynamic problems were identified. So for us, this is a great opportunity. While I kind of regret that Germany is phasing out of nuclear, for us as a training service provider, this is a great opportunity to bring our skills into the conventional side and do training simulators there.
Yeah, well, another challenge to grow business in another way.
Yes, and with the energy transition that we are facing, the whole system will change completely in Germany, as we have large generation systems, as we had large generation plants in the past. This will vanish completely. As you might know, we are looking for 100% renewable generation in 2050 with hydrogen backup plants there. So our customer base will change completely. And that is very challenging for us, but we're also looking forward to that. We will have smaller customer, we will have much more standardized plants that will be on the grid, and the training needs will change completely for this new energy system. And that is what we're currently adapting to. That is currently where we are changing our portfolio to accommodate these new types of plants that we will have in the grid.
I see, exciting. Jari, so you're coming from a technical research center, and I wonder what kind of innovations are you preparing in terms of training simulators for future?
One aspect that we have been interesting is to develop methods to assess or evaluate the results of training, because there are new opportunities for this kind of evaluation. For example, these new virtual reality-based systems provide new opportunities to collect information from training sessions, so that you can, for example, collect information where the operators are gazing, so that you could, for example, carry out these kind of retrospective think aloud sessions in which you show operators their scan pads when they monitor these screens, and we could ask them to think aloud what they have done and what they have thought when they carry out these particular operations. This is one option, and we have also used psychophysiological recording, so that we have information of the workload or stress, how distressed they are when they perform their operations. For example, we have carried out quite challenging scenarios in which there is a fire in the control room, or we could, for example, use also earthquakes or these kind of situations which are not possible to simulate in a physical control room. And then it's very important to get information of the operator's workload and how stressful they were. And so we could also show this kind of psychophysiological information, and show them, for example, using these kind of traffic lights symbols, so that if you are very distressed, there's a red light on the screen, and operators could tell how they feel and what they thought when they, for example, try to go out, walk out of the control room and to the this kind of control post, which is located outside the main control room. So there are new opportunities to collect information from operators' behavior after these simulator runs, and this information could be used for training purposes, so that operators could be asked to self-reflect what they taught and in some way this kind of self-confrontation method can be used for training purposes, so that operators have to thought about what they for example, if they have to make important decisions on what information this decision was based on, and how they solve a problem, particular operational problem in a challenging situation, so that they some way have to reflect what they have done, and this information can be then, and this kind of exercise can be very valuable to operators. This is one possibility, that we collect this kind of more richer information during these simulator sessions, and then, for example, present this information to operators when we discuss them in these kind of process tracing or debriefing sessions.
I see. I believe that no doubt, and that all of us agree that future of training simulators and simulation in general is very bright, and there are a lot of things that can be implemented to improve the trainings more. And this virtual reality, well, the imagination is our only limit. So I wonder, Ricardo, what is in your plans for future, and how you see future development for your virtual realities?
So you listen to me that I was talking about virtual reality innovation platform, okay? This is because, our first step when we jump into the virtual reality was, thinking on training. But, since the origin, we have evolved a lot the idea to the point that we are just now using virtual reality, not only for training, we are using virtual reality also for engineering activities like engineering design, prototypes, these kind of things, okay? And right now we are jumping into a new arena and we are looking at a solution. We are developing a concept to combine virtual reality, artificial intelligence, project management software, agile methodology, and machine learning in order to provide lean solutions to very challenging works, like, for example, the dismantle of a nuclear power plant. Okay, so we are working on that arena. It's very promising. We are very excited about the opportunity to continue adding new technologies to our portfolio of solutions. Okay, and we are wishing to continue learning about new opportunities to apply, because since we start this travel in July 2018 to nowadays, we have discovered a lot of different opportunities to use this kind of digital technology to make our life easier and to simplify our processes.
I see. Cash, from the user point of view, what are expectations for future development? And I mean, just seeing how these digital technologies are evolving, I believe that in 10 years from now, our future and how we use simulators will look totally different. And I wonder very often, where is the limit, and how are we going to be able to accept all that is coming in future? I mean, this virtual reality, it can be also scary sometimes, but here we are training, we are using it for training, you're using simulators to educate our people. What are expectations from you as a user, and what would be important for you to implement in future? I mean, in 5 years, some brighter future.
If I look across different countries, because I'm actually the chairman of an international working group that's creating a new ANSI standard 3.5.1, and that's to make use of simulators for simulation assisted engineering and non-operator training. Because typically at the moment we'd have, say we have 50 operations engineers that get trained on the main control room training simulator, but we don't provide similar level of hands-on training for the other, say, 400 or 500 people that are working on the power station. So there's tremendous scope for improving their productivity and avoiding unnecessary trips from maintenance and things like that. And also the nuclear industry has, I feel, has fallen behind other industries that have made much great use of simulators. For example, the aircraft industry, the motor car industry, the medical industry, etc. So there's tremendous scope for using simulators for nuclear industry simulation-assisted engineering to improve our engineering designs, so that we are able to make the existing nuclear power station designs, or those for new nuclear power station designs, much better than they have been in the past, so that there are fewer challenges to the main control room operators running the power station. And that way we can keep our nuclear power stations generating longer without unplanned trips and so on, because engineering is that much better behind it. Trip hardening, optimization of the plant, and checking out plant modifications on the simulator in advance, and finding out the problems that exist, which otherwise would not have been detected until the plant modification was made out of the plant, and then finding the problems at that time, which usually means you have to spend a lot more money, and it takes longer, etc. So simulation assisted engineering and non-operator training, in those areas, there's tremendous scope for improving the nuclear industry, because lots of our large nuclear power stations are having lifetime extensions, say in America and so on. So, for example, in some of the American nuclear power plants, they will be running for about, with various lifetime extensions, something like 80 to 100 years. And the new EPR designs that are being built at the moment, we're building Hinkley Point C EPR. That's going to have a design lifetime of 60 years. So with a few more lifetime extensions, that could typically go to 100 years as well. Mm-hmm. And then, of course, there's tremendous interest in the small modular reactors that are designed. And a lot of that design work is being done on engineering-grade simulators, let's put it that way, rather than the more simplified main control room simulators. So there's tremendous scope there to improve the nuclear industry in the forthcoming years.
A lot of room. Jari, what do you say? Are training simulators going to run the plants soon?
Yes, I think what I will continue what Kashmir say. I think the one possibility, one future ambition in what we is to use these training simulators and these virtual reality simulators in design, in control room design, and HMI design work. And one ambition is to one day validate the physical simulator by carry out these kind of verification and validation activities in a virtual reality control room. We have tried that, but Finnish nuclear regulator didn't accept our validation. When we carry out the integrated system validation in a virtual control room. But our ambition is one day to show that we are able to validate the physical simulator in a virtual world.
Yeah, exciting. Peter, we heard about your strategy moving from nuclear services and spreading in a wider circle. Would you like to add anything more to the strategy that you see in your company, the progress of training simulators and simulation in general?
Well, I would add, I would try to answer your first question a bit more than and add on what Jari said. I don't think that training simulators will run the plant in the future, but I think that a simulation will run together with the plant in the future. I see that this trend is coming. you know that there are digital twins for components already, but with the engineering grade simulators, as Kashmir just mentioned, this will open up the opportunity that we will have a whole digital twin of the plant running together in real time with the existing plant. And that can be used to look in areas where you don't have measurements in the plant. You can run it faster than the real plant to see where the plant is actually going to. You can rewind it to see what has happened in the past. And things like that will be done with simulations in the future, in the time span of 5 to 10 years. I would think that they will come online. And this is also something that we are doing some prototypes in that area. Very little proof of concepts to see if that is working. And this will be a very interesting use case for training simulators or then engineering simulators in the future.
Yeah, well, gentlemen, it has been a really pleasure to hear your thoughts and your experiences in your sectors where you are working. And I'm more than happy to conclude how we all see a future very bright, and integration of simulation on all levels, from process design, process optimization, data mining, predictive analytics, predictive maintenance, and of course, training simulators used for educational purposes. So here, I guess we will conclude this very interesting panel. Thank you for joining me and enjoy the rest of your conference. Thanks.